This video demonstrates the use of the OAI thigh segmentation GUI. We begin by choosing a patient to analyze using this drop-down menu. When we decide which patient we would like to analyze, we click the Load button, and the proper image and gradient map for that patient are shown on the right. We focus on the right thigh of each patient. First, in the analysis, we select a template, which is an image which closely matches the image we would like to segment. This template is chosen using a measure of similarity between grade level histograms of the image and the possible templates, known as the KL divergence. The template which shares the lowest KL divergence with the image we wish to segment is chosen as a template. We then extract point correspondences between the image and the template. These point correspondences are used to align the template to the image and therefore align the contours of the template to the image. We will use these contours as initializations for our segmentation procedure. We align the template, and you can see that the register alignment is much closer for an initialization than the initial alignment. Before we continue with our segmentation, we would like to pre-process the image we wish to segment in order to give the procedure a better chance of a successful segmentation. In order to improve the chances of success, we need to perform procedures that will highlight the edges between contrasting tissues and reduce edges that might appear within the same tissues. First step is to reduce the arterial artifact, which can be seen here. This is caused by blood flow through the femoral artery. The corresponding image and gradient map are again shown at the right. Next, we reduce the intramuscular fat, which can be seen as thin, high-intensity lines within muscle. We then reduce the bias field, which can be seen here. This dark area of subcutaneous fat differs in intensity from this brighter area of subcutaneous fat, although they represent the same tissue type. We reduce this bias field through a process called homomorphic filtering. We then smooth the resulting image using anisotropic diffusion. One can see that edges between contrasting tissues are enhanced, while edges within the same tissue are reduced or removed. Finally, we remove the background and we remove the femur. We segment the muscles starting with the rectus femoris. The segmentation procedure consists of a contraction phase where the initial muscle contour is contracted to try to wrap around the correct muscle. It is followed by an expansion phase, which will hopefully improve the segmentation. The results are listed in this panel at the bottom here, and they're based on the Zij-Denbos Similarity Index, which is a number from 0 to 1, with 1 being a good agreement between a manual and an automated segmentation. We continue with the vastus intermedius. The vastus intermedius initialization takes advantage of the previous segmentation of the rectus femoris. The expansion phase concludes after 300 iterations, and the corresponding ZSI is shown in the panel. A ZSI of 0.7 is deemed to be excellent agreement. The vastus lateralis is performed next. can be seen that the contraction and expansion phases cause a successful segmentation. The vastus medialis is done finally. And the corresponding ZSI is shown in the box. The ZSI average of 0.9 is excellent.